And last but not the least, Ankur Moitra, how robust are thresholds for community detection?
Great, thanks. So I'm going to be talking about joint work with Amelia Perry and Alex Wine. So I'm a theoretical computer scientist who spends a lot of time thinking about what are the algorithmic foundations of machine learning. But also a lot of my work connects different areas. So I thought it would be fun to tell you about some work that discusses what happens when the areas of theoretical computer science and statistical physics collide with each other, and how can we make sense of their different perspectives. So the first thing I'm going to do is I'm going to tell you a story about community detection, which is really a story about the success of belief propagation and predictions made within statistical physics. So what is community detection? Well, roughly it's the goal of trying to find well-connected sets of nodes within a larger graph. Usually the way that these problems are studied is through the stochastic block model, which is a generative model which was introduced over 30 years ago, which is the following procedure for generating a random graph. You start off with every node being labeled with one of k different communities. I'll use colors to denote them in this talk. And then you have a k by k matrix of connection probabilities. So for example, the entry in row 2, column 1 is the probability that if I have a node which is red and a node which is blue, that they're connected by an edge. So all you do is you sample edges independently according to these given probabilities. This is a way of generating a random graph in which there's a planted community structure where some sets of nodes are well connected within themselves than they are to the rest of the graph. So this simple ubiquitous model has been studied for decades within statistics and computer science, and more recently in information theory and statistical physics, where the goals are to get to the fundamental limits of the problem. Now, in fact, not only has this problem been studied by a very diverse range of fields, there are even a diverse range of algorithmic techniques that have been brought to bear on these problems. Things like combinatorial methods, like simple degree counting, spectral methods, where you take an eigendecomposition of the adjacency matrix to find the community structure, MCMC techniques, and semi-definite programming. All of these different types of algorithms can give provable guarantees that they really can recover the underlying community structure in some ranges of parameters. But actually the main actor in the story is going to be a different algorithmic technique, one which comes from statistical reasoning due to Judea Pearl, called belief propagation. In fact, when Pearl introduced this in 1982, he later went on to win the Turing Award a few years ago, which was in large part for belief propagation and many of his other contributions to probabilistic and causal reasoning. So let me tell you at a high level what belief propagation is when it's applied to community detection. All it is a simple iterative algorithm in which every node maintains some beliefs about the probability they belong to different communities. So each node has, at each time step, has some probability he thinks he's different, belongs to different communities. And what happens is you just broadcast your beliefs to everyone. And each person collects all of these other beliefs being broadcast to him, and he uses that information, plus whether he's connected by an edge or not, to update his own beliefs, and then he sends his beliefs back out to the rest of the world. So you just do this iterative procedure where you converge to some sort of consistent beliefs about the probabilities you belong to different communities, and this is one of the landmark algorithms within statistical physics. Now, as I mentioned, recently there's been a lot of emphasis revisiting community detection and trying to say not just what are algorithms that work, but what are algorithms that work down to the very limits of the problem. So one special case, which is really an easy setting of community detection, is let's make the problem as simple as possible. There are just going to be two communities, and they're going to have the same size. So I have the red community and the blue community, and within each community, I'm going to connect every pair of nodes with probability A over n, and between the two communities, I'm going to connect with probability B over n. And you should think about A and B as being constant here so that you generate a sparse graph. Now, usually the goal is to try and find the underlying community structure from this random graph. I do want to mention one technicality, which is actually important, which is if you think about A and B as being constants, then you're likely to get a constant fraction of the nodes are just going to be disconnected. So you have no information about what communities they belong to because they connect to nothing else in the graph. So your goal isn't to find every label correctly, but is to do better than random guessing. So in fact, the conjecture that came out of statistical physics is a remarkably sharp conjecture, is that it's possible to find a partition that's correlated with the true community structure if and only if a minus b squared is larger than 2a plus b. In fact, the way that they arrived at this conjecture was through belief propagation. There's a trivial fixed point of belief propagation, which is where no one knows anything. And all you do is you start off thinking that I'm equally likely to be either of the two communities, and you keep broadcasting nothing to everyone else, and you never learn anything. But when this condition on A and B hold, that trivial fixed point becomes unstable. So the belief was that if belief propagation doesn't get stuck at the trivial fixed point, then whatever it finds must actually have some agreement with the true community structure, and that if belief propagation doesn't work, that it must be not a failure of belief propagation, but because the problem is fundamentally information theoretically impossible. So this is a wildly bold set of conjectures. It should sound that way. And what's kind of amazing about this is that the conjecture is true. So this shocked me. This is some really neat work of Mossel, Niemann, and Sly, and independently by Masuli, who proved that that is exactly the information theoretic limit for the problem. Not only that, but there's an algorithm meeting that bound, which really comes from belief propagation, really a linearization of belief propagation. So as I mentioned, I'm a theoretical computer scientist, and this looks very strange to me because things like belief propagation may be the champion algorithms within statistical physics, but when we talk about algorithm design, the main paradigms we work with are things like convex programs, and in particular semi-definite programs. So even though those things work well, they get down to a minus b squared is larger than some constant times a plus b, it works for a constant that's strictly larger than 2. So it doesn't get down to this information theoretic limits of the problem. So at this point, we're forced to ask some broad philosophical questions. For example, are these non-convex approaches, for example, arising through belief propagation, are they just fundamentally better than convex methods and convex relaxations? What's going on here? Or even better, increasingly, as both theoretical computer science and statistics and machine learning and statistical physics start thinking about average case problems, we start treading on each other's territory. So what happens when there's a problem which we all care about, and methods of statistical physics which make some predictions make different predictions than what's our form of evidence within theoretical computer science, things like semi-definite programs? Who's right and who's wrong? Well, I'm going to tell you a way to reconcile these differences, which really comes down to a different language that they're speaking. So the final character in this story is a refinement to community detection, which is called the semi-random model. These are models which are very popular in theoretical computer science. I think these are important models going forward in a lot of different other communities, not just in theory. These are introduced by Blum and Spencer and refined by Feige and Gillian. And what you do is you sample a graph from the stochastic block model, but now you allow a helpful adversary to make changes that sound like they make your job easier. So this adversary sees the graph sampled from it, and what he's allowed to do is he's allowed to add edges within a community and delete edges crossing it. So he can do changes like this, and he can do changes like this. So all he's doing is he's making the communities, which are well connected, even better connected, and he's destroying some of the connections between the two different communities. But what's interesting about these types of models is that they prevent you from overfitting to one particular distribution. So when you choose a generative model, there are all sorts of regularity properties about nodes having almost the same number of neighbors in common in dense settings that all of a sudden you can't rely on in algorithm design. So it forces you to cope with the fact that you can't work on just one and only one distribution in order to solve these types of problems. So now I can tell you our main result, which is that actually, despite the fact that these changes sound like they're helpful, there's a way to make them hurt. So it turns out that if you design the semi-random adversary in just the right way, what you can do is you can make community detection strictly information theoretically harder. So there's a constant which is larger than 2, so that even though the threshold for the original generative model was 2, well, under the semi-random changes, you can actually destroy the structure, and the threshold of the problem still becomes impossible even when C is larger than 2. So this result actually bears a little bit of interpretation. I'm not going to prove it for you. But one of the things that this tells you is that when you have an algorithm that meets this information theoretic threshold, well then the reason that it works all the way down to the threshold has to be using somewhat brittle properties of the generative model. Because any algorithm that meets that threshold has to have its guarantees decay and break as you add these types of changes that sound like they help. So you're relying not only on the structure of the signal, but even the precise distributional assumptions about the noise in order to reach these types of thresholds. But more importantly, it tells us something edifying about what happens when theory and statistical physics start talking about the same problems. So things like semi-definite programs are designed to be somewhat robust. So in fact, you can show that the analyses of SDPs that show that they work for community detection continue to work under these monotone changes. Once they find the community structure, they continue to find it as you make it stand out more and more. So even though they make different predictions, it's really because they're talking about different problems. Statistical physics is a very sharp prediction about one family of distributions, and by the way that we reason about semi-definite programs, they tend to be ways to reason about families of distributions, all of the things that you get from these monotone changes, and there really can be harder problems hidden inside that entire set. And actually, despite the fact that semi-random models have been studied for over 20 years, this is actually the first separation between random and semi-random. This is the first instance of a problem which is possible in the random setting, which becomes information theoretically possible under semi-random changes. In the past, all of the problems that were studied, once we had algorithms that worked in the random case, it turned out that there were things that did work in the semi-random case, usually SDPs. So just to take a little bit of a broader perspective, you can go further and study all sorts of other sharp threshold models. An even easier problem, which I'm not going to define, is something about reconstruction on trees, which has to do with phylogenetic reconstruction. Sometimes it's called the broadcast model. And some old thresholds, which are called the Kesten-Stigam bound, tell you that the right way to recover the roots label from the leaves is just to take a naive majority vote. But there's this gap between the theory and the practice, which is that a lot of times what people use in practice is something called recursive majority. That doesn't reach the threshold that majority reaches. So you could wonder, why are people using this despite the fact that the theory for what's the right way to get down to the threshold has been known for over 50 years? And our answer to this question is actually the same, is that because recursive majority works in a semi-random model and majority does not, it fails spectacularly. So what this raises is an interesting philosophical question, which is when we try and reach the sharp information theoretic thresholds of a problem, is that really the right goal to begin with? To what extent are these sharp thresholds a property of exploiting not only the structure of the signal in a generative model, but even the precise structure of the noise? And taking even one more step back, within theoretical computer science, there's a lot of excitement these days on something called beyond worst case analysis, which was hinted to, for example, in Philippe's talk. When we start off with problems, which we study them in the worst case, we get these very pessimistic views that everything is hard. So what people study is they try and study something that's beneath worst case analysis, which makes the problem a bit easier so that you can be optimistic from an algorithmic design standpoint. These are famous works, for example, of Spielman and Tang studying things like the smooth analysis model, which is a goal of trying to explain why algorithms that have poor worst case behavior do work well in practice. But let me offer a different way to think about this, which is maybe these semi-random models, which were studied within theory under the name of beyond worst case analysis, the right way to think about them is not beneath worst case analysis, but is above average case analysis. So there's a lot of work which is perfectly happy making a distributional assumption, and then we prove various algorithms work under distributional assumptions, things like matrix completion, where we have a variety of techniques that have provable guarantees. But then we lose sight of this other axis of comparison, which is some of the techniques tend to be more robust to model misspecification than the others do. So can things like semi-random models be an interesting way to explore a different axis of algorithm design, namely what happens above average case analysis to prevent you from overexploiting your precise distributional model? All right, so I'll end there. Thanks for your attention. Thanks. Any questions?
Have time for one or two quick questions, Deborah.
So, in the context of the block model, do you observe the similar sort of change of the instability point for belief propagation from 2? Let me sort of give context, because at least in a variety of cases, either belief propagation has found while it comes as a heuristic, it has found some connections to some form of optimization relaxations or spectral methods or variations of spectral methods. So it's not clear that sort of it's not brittle. Or
That's right. So that's an interesting question. So I don't know exactly the answer to that question, but the high temperature limits of these things turn out to be, for example, when you look at the local structure in the graph, you get these majority vote, types of things about reconstructing the route from what's happening in a neighborhood outside it. And those types of things, when you actually do these perturbations, not only do those points become they don't accidentally become stable, but they just have wildly bad properties. So you can make, based on your semi-random model and what your adversary does, you can essentially control so much of the tree that you can make belief propagation think whatever you want it to think. Essentially because it uses paths entirely, which have long changes between the colors, and those are things which you have control over as an adversary.
Other questions? Yes?
So do we get anything from aggregating like belief propagation and the other method or SDPs, or are they is one strictly worse than the other in all domains?
So it depends because, there are also many ways to study things like model misspecification. So you see here, the changes were entirely monotone, that they sounded like they were going to help you. That's why we chose this model was because then it's not obvious that these changes actually change the information theoretic threshold. But a lot of times people also study it when you're allowed some bounded number of changes where you can, change a constant fraction of the edges. And there it really would change the information theoretic threshold because you could, for example, just delete edges that are supposed to help you and are within the community and make things harder. So partially, these things become a little bit incomparable because what are the right thresholds depends on how exactly you choose the model. So I don't yet know of any way to really say that an SDP or belief propagation, one dominates the other. This is more of just a starting point for what are the ways in which they have incomparable strengths than it is to say that one is definitely better or not. But thanks.
Good. I think we should wrap up and whatever questions push to the much-deserved coffee break. I want to thank Ankur and all the speakers for being incredibly disciplined, but also, most importantly, for the great content. Thank you.